Uh, Thank you for having me here. So I am Daniel, or you can call me Yanjun, and I am presenting this work from our Gerstein's lab at Yale University with Japan, Jiwon, Robert, and Professor Mark Gerstein. So today we are talking about a strategic question in medical AI, like whether we should use agentic workflow or whether we should only use the single reasoning models alone. And we will answer this question through a rigorous benchmarking study on complex reasoning, clinical reasoning problem. And specifically, I would talk about three things, like how to evaluate clinical reasoning models beyond the ceiling effect of the existing benchmarks, how to fairly compare reasoning models and agent frameworks under cost and latency constraints, and how to identify when agentic complexity actually helps. So let me briefly introduce myself. I am currently studying my master's degree at Yale University in computational biology, and I did my bachelor's degree at Fudan University. So my earlier work was mostly focusing on the HPC and distributed training for large language models, but later on I've been working towards more into the field of AI for biology, or especially the AI for biomedical discovery. So that's why I work a lot on the different kind of biomedical data, including this kind of medical AI and benchmarks. Then I will spend most of the time talking about our existing medical AI benchmarks, as well as our MedAgentsBench, which is the main topic of this talk. Probably if we still have time, I will go over the latest model that we built on top of the MedAgentsBench, which is called MedAgent X. It's a evidence-based medical reasoning framework. Yeah, so let me start with some basic backgrounds. As you guys might know that nowadays, people can actually ask questions to GPT or to any kind of LLMs on the clinical problems. And they can just put into the chat into, like, for example, like describe your clinical situation. And the clinical reasoning is actually mostly a multi-step process. Let's, for example, look at this. It's just some description of a patient who is a man that goes into the emergency department and having some fever, and he want the doctor to give some diagnosis. So what people usually do is to, or the doctor usually do is to do multi-step reasoning, where you will first identify the patient presentation, and then look at the typical organisms, and then review the most relevant diagnosis and give a final answer. So this is just a very easy example, but real clinical decisions often much more involved, more reasoning is involved. So but for a long time ago, actually, this medical AI field has evolved significantly. So at first, from the era of the GPT-3, we have shown basic medical knowledge, or the medical ability in earliest in 2020, and people have been working on a lot of things like BioBird or MedBird or something like that to encode medical knowledge. And later on, there's a really impressive foundation model from Google where they present MedPalm, and they show that a large language model alone actually encode a lot of clinical knowledge, and they can do medical question answering pretty well. So later on, a paper from our lab, from Gerstein's lab, we we developed first multi-agent system based on the large language models to specifically adapt to the clinical domain and do the clinical question answering. And later on, there are more and more follow-up works which pretty much use the similar architecture like the multi-agent discussion and kind of voting mechanism or report generation to answer the clinical questions. But here comes a question like, are the LLM agents itself really help the clinical decision support system or the clinical reasoning process? Isn't that because the base language model has evolved over time that leads to their superior performance? And meanwhile, there are a lot of paper that benchmark the different LLMs and base LLMs, but actually few of them, like most of them are published in some major journals such as like the Natural Medicine or Cell Patterns, or there are some paper from OpenAI that did some holistic evaluation. But most of them are doing benchmarks on the LLMs alone, but not too many of them worked on or talk about the differences between the different agentic frameworks. And so here comes our design, like how we design our benchmark for the medical question answering. So the first problem of all of these medical benchmark is probably the ceiling effect, where a very popular benchmark called MedQA, which is some multiple choice questions in the medical domain. It's one of the first work in this field, and people have benchmarked on it for a long time. And it seems nowadays that the best model itself is scoring above 93%, which means the model could, like a very simple base model, could answer 93% of the questions right. Or in other words, you only have 7% of the questions that are not solvable by those base models. So at this point, you actually cannot meaningfully distinguish between different kind of reasoning approaches, because those approaches are like having a 0.1, 0.2 differences between different methods. So it's hard to distinguish anything or make any good conclusions. And also there's another small discovery from my side, is that actually why those MedQA or the models on MedQA couldn't go beyond 94% is because actually 6% of questions are not valid, where they're missing images or they are fundamentally wrong. So we have to filter out these questions to make the medical benchmark more reliable. And actually, we need a more careful design of medical benchmarks. So here comes the first idea. We just need to collect more medical AI benchmarks from the existing literature. For example, we have 2019, we have the PubMed QA, we have 2020, we have the MedQA, and 2021, which is a very good year for language model evaluation. There is a task called MMLU, and later on 2025, there's a very expert curated data set called MedExpert So it looks very good because we have multiple level and higher quality and more difficult questions collected in our setting. So therefore, we can actually do some benchmark over the base models. And here comes the result. It seems that we have a lot of differences between the different models, which is a very good sign of this benchmark, because we can actually use this benchmark to differentiate or distinguish the different performances. But however, this is still have some big problems, because total, like when we collect the data set in total, it will give us around like 10,000 different questions. And since we are going to benchmark whether agent method or agentic system are useful or not. We have to run those agentic system on so many questions, and these benchmark summing together, we probably have more than 10,000 questions. And we, as we have like benchmark or profile the actual cost of running this kind of agent system. For each question, you probably have to spend over half a dollar or 50 cents per question. And so in the end, after doing a simple multiplication, it seems that our experiment will take $5,000 to run, which is quite costly. And if other people want to replicate this experiment, they will have to pay the same price. So we need to have a representative subset that are both challenging and cost effective. So here's our approach. And think about a simple way. We just run a diverse family of 10 base models across all the questions. And if all of them are answered doing the answer correctly, then probably this question is too easy. And if some of them are good, but some of them fail to answer, then we would say that this question is quite representative, because it could actually say, hey, how we have specific model is good at doing this, but some models are not. We also found that some questions are really hard to answer, that and none of the existing LLMs could answer it correctly. So we'll have a question that these questions are either too hard for the clinical system, or the question is fundamentally wrong. So we did this kind of heuristic filtering to reduce the number of the questions that we have to annotate. So because we always have to annotate all the questions before, like we have to use a human to annotate all the questions in the end. So yeah, so this is kind of a difficulty screening, and we can see that a lot of the benchmarks actually have plentiful questions that satisfy our criteria. Our criteria is just like setting half of the models could answer correctly and half of them cannot. So those goes beyond half is called a hard question. And we're going to look into the details of the hard questions. So here comes the actual construction pipeline, where we actually hire 3 practicing clinicians, where they annotate the reasoning depth of the question. At the same time, they also evaluate whether this question is correct or not, based on their internal understanding. So basically, the 3 clinicians will have a separate or individual independent annotation process, and they will have them combined together with some kind of Cohen corpora. And we did this kind of annotation very clearly, and we see that there are different levels of clinical reasoning. For example, there are some questions, mostly from MedMCQA, where people only ask about some facts in the clinical decision system, and most questions in MedQA or MedBullet, there are a lot of reasoning depth, where people the questions are usually about some rare disease case, and the LM should or the clinicians should actually reason over these questions and get a final answer. So after this kind of annotation, we actually picked very nice reasoning depths out of the full original set. So you can see that after the statistic, the hard set has a huge improvement in terms of the reasoning depths. So in the end, we roughly picked around 862 carefully curated hard questions. And in the end, the total experimental cost drops to under 400 per run. And actually, we didn't even spend so much money because the actual execution pipeline is still kind of optimized. So we made it the systematic agentic evaluation feasible for the first time. And so there is another problem of the agentic evaluation. So as I said, like the agentic framework is kind of a model agnostic. So it doesn't depend on which good base model you choose, but in order to benchmark them fairly, we need to fix the base model we use in the agentic discovery pipeline. So we have to think about some problem. If the base model is highly data contaminated, where it is a very popular problem that in this field that those kind of models or LLMs tend to recite or memorize the questions in a system. So this is a very dangerous thing, because if your base model is already know what is the question, already know what is the answer, then the final score doesn't look very good to you, right? So that's why we use this kind of heuristic, still a heuristic based detector, where we put into the model a question, and we mask the second half of the question, and we ask the model to complete it. So we have different models doing a different kind of completion. And for example, you can see the O1 mini, it goes into a different direction and say some different things against the original completion. However, the DeepSeek R1 is prone to have some similar patterns of words. For example, it used is associated with against the ground truth. So basically, we use the Levenstein detector, where is the added distance between the generated words and the ground truth. So we can calculate whether the model could actually memorize the data. And surprisingly, the OpenAI model shows consistently lower memorization scores across all the data sets, while the other open source models such as DeepSeek R1 or Qwen or Llama or even Cloud, they show substantially higher similarity between the generated and the ground truth sequences. Sometimes sometimes those similarities are exceeding 95% on the benchmarks such as the MMLU in the DeepSeek R1 cases. So basically, it's just memorizing the whole thing. It's not doing any reasoning. And that's why we tend to choose the GPT-4o or GPT-4o mini as a base model for our agent evaluation. So basically, think about the causal inference problem about the performance of the actual agentic system. We want to minimize the unfair advantages across the data contamination. So that's why actually we also benchmark on O1 and O3 mini. Yeah, and so let us go deeper into the MedAgents benchmark, and let me introduce the different contenders of this kind of competition. So we basically organize them into three paradigms, where there are base models such as the GPT-4o and Cloud, the general purpose single forward pass. But reasoning models such as DeepSeek R1 and O3 mini, they are trained with reinforcement learning to internalize the chain of thought reasoning ability. Or you can see that most of the reasoning model, they have a special thinking token. And in the thinking token, between the two thinking tokens, they will generate a long chain of thought. And also we have different forms of agentic frameworks, from the discussion-based systems, or they're designed specifically for medical discussion, such as the MedAgents or MDAgents, as we said before. And also we found that recently people are using some automated workflow design, for example, the A flow or SPO, where you have defined a clear problem and let the model to discover the best component of the agent system. So basically, it's a more advanced and cost-effective way to do the agentic design. And also, we have a lot of baseline methods such as self-refine or chain of thought or multi-persona, which are the kind of a prompting method or like a very baseline prompting method. So there are three different types of the medical AI system, and we are actually looking to see if the agent framers actually could outperform the reasoning models, or at least they can outperform the base models. And so let's see the results for the base models or the reasoning models. And you can see that reasoning models always dominates the benchmark against the base models. So you can see that even on our hard benchmark, the DeepSeek R1 and O3 Mini consistently outperform all the non-reasoning models by 15 to 25 percentage points. For example, in the MathQA hard, O3 Mini scores 53, while GPT-4 only scores 32. And the internalized reasoning capability makes a massive difference on generally difficult clinical questions. But when we compare the agentic methods, the differences are still harder to see. You can see that only the A flow, which is the automatic searches over the reasoning workflow, performs best overall. But the gains over simpler methods such as the chain of thought or multi-agent frameworks such as the MedAgents or MD agents, they actually don't beat the reasoning models. But actually, if you look at the reasoning cost, they spend you have to spend like 5 or 10 times significantly more amount of budget on the reasoning process. So here comes the very key conclusion that probably agent framers, they're offering a diminishing return while layer on the top on top of the originally strong base models. And to further verify this, we plot the Pareto frontier plot. So this is basically we put the model on their past one accuracy as well as the cost in terms of the API calculation. So the red dash is actually showing the optimal cost performance trade-off, where all the dots on the Pareto frontier, you can say that they are good enough to use. But those models that falls behind the frontier, you might say that they are not a good contender to choose. So you can see that DeepSeek R1 actually with a very basic prompting or O3 Mini with a basic prompting, they sit on top of the Pareto frontier, while some kind of weaker models such as the GPT-4o Mini, which has no reasoning capability, even if you equip them with the strong agentic systems such as the MedAgents, where they claim in a paper, or the MD agents, you cannot put them high enough compared with using a stronger base model. So to summarize the benchmarking results, the reasoning models often win on accuracy, and workflow optimization models such as A-Flow, they win on the efficiency. But however, like the multi-agent or the so-called multi-agent pipeline, you might have to adopt them selectively, and it is not by default the best method in this case. And we also as we have run a lot of baselines and method. We have a lot of output of the models, and actually we can did we could do a very comprehensive qualitative error analysis, and we found that there are actually three groups of recurring failure patterns. For example, the first one is called overthinking, where it is usually happening in the reasoning models such as the DeepSeek R1. You can see from as a figure is that it's continuously saying however, or let's do it again, or rethinking, and then after they think again and again, actually they abandon the earlier correct answers, but uh, like after excessive deliberation, and you don't give them a clear convergence criteria. They just keep talking to themselves and then making everything worse. And the second possible error type is the group bias, where mostly happens in the multi-agent systems such as the multi-persona. They actually amplify the shared biases where agents they independently do the analysis on the clinical questions, but they finally converge to the same wrong conclusion without any mechanism to detect the disagreement between them. So people tend to have the same opinion. This is also true in a real human world, but it is also something that we discover in the multi-agent system. And the third, and also motivates us to do a new method is those kind of iterative refinement methods, such as meta-agents or self-refine. They cannot exceed the base model's existing knowledge. So if you don't have external information or um, like external clinical resources to validate the proof or the conclusion of the model, then the self feedback don't usually have the opportunity to correct themselves. Therefore, we to summarize, we need to build some models that could have the iterative refinement, but you also have the access to the external resources. And also for the group, you need to have different opinions instead of asking them to do the same thing. So basically, like the composition of your reasoning team or the multi-agent system should also be quite flexible or diverse. So that's some motivation to our next contribution, is which is a new multi-agent framework that is specifically designed to address these issues. So here we introduce MedAgents X, where it's uh, moving from a simple collaboration to real and accountable deliberation. And this framework has four key components. The first is the clinical triage, where, as I said, we need a more diverse team of experts to provide us with different opinions. And we have the evidence grounded reasoning, where the agent could look into external resources such as PubMed or StatPers or other clinical literature to give them more evidence and external reasoning ability. And third, we also introduced some multi-round discussion mechanism with a carefully designed weighted voting to reach the final consensus. And so as we did the benchmark again, we saw that our MedAgents X is actually so like it's a manually implemented framework, but it seems that this manually implemented framework actually performs better than those automated search baselines, as well as the old baselines such as the MedAgents or MD agents. and I will later briefly walk you through how this works, because I'm still like working on this paper and we don't have a very concrete or too concrete method development. So yeah, we can go through a running example where a 52-year-old woman reported some kind of worms over her face and trunk. So you can see that it's not a very common question, but we can ask the clinicians to do a different kind of triage, and the triage agent will give so so it will see that this question is probably very hard, and it will dynamically allocate 5 different doctors in a sense, and it will actually ask for 5 different doctors that are relevant to this field and assign a different weight to each doctor. So as we see, it recruits a cardiologist, internalist, and an emergency medicine physician, and each with the assigned weights. And the moderator, so this is still like we create a specific profile for each of the doctors. So we have where it graduate from, what is specific expertise, technical skills, and also like how many like we just create this in situ or virtual profile of the doctor. And we also have a general moderator where the moderator sets the structure agenda for discussion, where we have different recommendation for what to discuss in the next step. And so basically with these single agent with their profile, we also enabled the medical evidence retrieval using a very state-of-the-art model called MedCPT, where it's trained on a large corpus of PubMed search queries and articles. So this gives all of these agents ability to look for the external resources. And in the first round, they will look into some relevant but different resources, because we have different agents and their expertise are actually different. So we have different evidence and then give different rationale. And so in the first round, most of the agents have different opinions. However, after that, that's why the moderator's role becomes critical. So after a first round, the moderator looks into the differences in the retrieved sources and the opinion of the agent. And the moderator is quite fair, so it identifies what agents or each doctor is missing. So it looks like some medical tumor board where the clinical director will hire a group of doctors and then talk to them. And so they will see that some of them are not using the consistent guidelines or something like that. And then the director will go into the next step where he will ask those clinicians to synthesize the evidence again based on their limitation and reassess the strategy. And after several steps of discussion, we will see that there are different kind of team structures and different kind of deliberation styles, where we can see that there's such kind of a moderated meeting where moderator is involved in the discussion, and the different doctors reporting to them actually have the best performance in terms of the benchmark results. And with this kind of voting mechanism, we can have a concrete answer for each round of discussion. So after that, we have to arrive at the final diagnosis. And yeah, so the patient is hopefully recovered. And so where we originally at the MedAgentsBench, we are also caring about the cost-effective performance across the different models and different scales. And we look at this complicated medical agent framework. It actually, you can see that it has the evidence retrieval and multi-round discussion and voting. It's quite complicated, but it seems that the final cost is not as much as those original agent, and also it's not too much against the search baselines or simpler baselines. So we would say that this MedAgents is a very good application of this benchmark, and we're still working on it to improve its mechanism or the understanding of the medical questions. And that's all for my talk. And yeah, and is there any questions?
Okay, thank you so much, Anu. That was a great presentation. Well, if anyone has any questions, you can unmute yourself or you can post in the chat.
Sorry, is there anything?
No, there's any question in the chat. Okay, in the meantime, I can ask. I have a question. So in this multi-step diagnosis, do you see there's some, it's basically a single hallucinated reasoning step can derail the entire treatment plan, right? So does MedAgentsBench penalize models for correct final answers that were reduced to a flawed logic? Do you have that kind of setup within MedAgentsBench in terms of addressing hallucinations?
You mean like the hallucination in the the benchmarks, right?
Yeah, basically, if it's penalizing the models for the correct final answers, that leads to some flawed logic. It's not the right logic, basically.
I see. So, I think this is a question. It's a good problem of our benchmark, but we didn't look into on the hallucination aspect. I think there are some potential works in this field in the LM fields to reduce hallucination. For example, you look into the logics of different LLMs or sample them multiple times, or doing some kind of confidence based method, and then you can have a kind of clear reduction in the hallucination. But also, as I said, we have the evidence-based retrieval. So this could give you more of a factual relevance, or you can retrieve more facts against the with the external references. So yeah, there are a lot of approaches to reduce hallucination, but we haven't worked on that for a long.
Just seeing if there are any questions. Yeah, if anyone has questions, if you can put it on the chat, I can read it out. If not, maybe we can end the call earlier first.
Sorry, I didn't hear that clearly.
No, I was just saying, if anyone has questions, they can put it in the chat. I'll just send it to everyone.
Okay, yeah.
Okay, we have a question. If the benchmark only includes hard questions, is this a problem? I mean, what if the agent makes a silly mistake?
So that's why we designed this benchmark. We want to actually encourage the agent to make mistakes where we are able to make the distinction between different agents. Yeah, we're not using the benchmark to develop some kind of medical assistant support. We're using the benchmark to evaluate the ability of the medical agents. So this is the general setting and the idea behind why we need this benchmark.
So how are you categorizing the hard questions? So is it like I know that you mentioned you're hiring clinicians to do the scoring, right? So how do you, in terms of, because different clinicians might come up with different way of interpreting it. So how is there any consensus in terms of how you're coming to a common conclusion that okay, this is going to be hard, it's going to be easy, or maybe.
So we are taking asking the clinician to annotate each questions, and they have so everyone will set a score. For example, for the reasoning depth, it's 1, 2, 3, 4, 5. So on scale of 1 to 5, and then we just calculate the Cohen kappa against each other, and so that's how we we saw that actually the different annotation are quite similar because the questions are actually having a good quality. So yeah, and I remember there was like around 6 different questions that are fundamentally wrong, and like 20 or something questions they require an image as an input, but there was no image given in the original benchmark, so we exclude all of them, and actually all the annotators they agree to remove those, so we didn't even check more of the details.
Okay. And I didn't see any more questions. I guess we can end the call here, I guess.
Yeah.
Yeah. All right. Thank you so much, Daniel. That was a very interesting presentation. That if anyone has any questions, you can reach out to him. Yeah.
Yeah. Thank you, everyone.
Thank you, everyone. Bye.